is to cooking, kinesiology is to dancing, and grammar is to writing. The idea here is that you can be a wonderful cook without knowing any chemistry. But if you know some chemistry, it's going to help. You can be a wonderful dancer without knowing kinesiology, but it's going to help. And you can probably be a good writer without having an explicit knowledge of grammar, but it's going to make a big difference. The same thing is true of data science. You will do it better if you have some of the foundational information. So the next question is, what kinds of math do you need for data science? Well, there's a few answers to that. Number one is algebra. You need some elementary algebra. That's the basically simple stuff. You can have to do some linear or matrix algebra because that's the foundation of a lot of the calculations. And you can also have systems of linear equations where you're trying to solve several equations all at once. It's a tricky thing to do in theory, but this is one of the things that's actually easier to do by hand sometimes. Now, there's more math. You can get some calculus. You can get some big O, which has to do with the order of a function, which has to do with sort of how fast it works. Probability theory can be important. And then Bayes' theorem, which is a way of getting what's called a posterior probability, can also be a really helpful tool for answering some fundamental questions in data science. So in sum, a little bit of math can help you make informed choices when planning your analyses. Very significantly, it can help you find the problems and fix them when things aren't going right. It's the ability to look under the hood that makes a difference. And then truthfully, some mathematical procedures like systems of linear equations, that can even be done by hand, sometimes faster than you can do with a computer. So you can save yourself some time and some effort and move ahead more quickly towards your goal of insight. Now, data science wouldn't be data science and its methods without a little bit of statistics. So I'm going to give you a brief statistics overview here of how things work in data science. Now, you can think of statistics as really an attempt to find order in chaos, find patterns in an overwhelming mess, sort of like trying to see the forest and the trees. Now, let's go back to our little Venn diagram here. We recently had math and stats here in the top corner. We're going to go back to talking about stats in particular. What you're trying to do here, one thing is to explore your data. You can have exploratory graphics because we're visual people and it's usually easiest to see things. You can have exploratory statistics, a numerical exploration of the data. And you can have descriptive statistics, which are the things that most people would have talked about when they took a statistics class in college, if they did that. Next, there's inference. I've got smoke here because you can infer things about the wind and the air movement by looking at patterns in smoke. The idea here is that you're trying to take information from samples and infer something about a population. You're trying to go from one source to another. One common version of this is hypothesis testing. Another common version is estimation, sometimes called confidence intervals. There are other ways to do it, but all of these let you go beyond the data at hand to making larger conclusions. Now, one interesting thing about statistics is you're going to have to be concerned with some of the details and arranging things just so. For instance, you get to do something like feature selection. That's picking variables that should be included or combinations. And there are problems that can come up. There are frequent problems, and I'll address some of those in later videos. There's also the matter of validation. When you create a statistical model, you have to see if it actually is accurate. Hopefully you have enough data that you can have a holdout sample and do that, or you can replicate the study. And then there's the choice of estimators that you use, how you actually get the coefficients or the combinations in your model. And then there's ways of assessing how well your model fits the data. All of these are issues that I'll address briefly when we talk about statistical analysis at greater length. Now, I do want to mention one thing in particular here, and I just call this beware the trolls. There are people out there who will tell you that if you don't do things exactly the way they say to do it, that your analysis is meaningless, that your data is junk, and you've lost all your time. You know what? They're trolls. So the idea here is don't listen to that. You can make enough of an informed decision on your own to go ahead and do an analysis that is still useful. Probably one of the most important things to think about in this is this wonderful quote from a very famous statistician that says, all models or all statistical models are wrong, but some are useful. And so the question isn't whether you're technically right or you have some sort of level of intellectual purity, but whether you've done something that is useful. That, by the way, comes from George Box. And I like to think of it basically as this, as wave your flag, wave your do-it-yourself flag, and just take pride in what you're able to accomplish, even when there are people who may be criticizing it. Go ahead, you're doing something, go do it. And so in sum, statistics allow you to explore and describe your data. They allow you to infer things about the population. There's a lot of choices available, a lot of procedures, but no matter what you do, the goal is useful insight. Keep your eyes on that goal and you will find something meaningful and useful in your data to help you in your own research and projects. Let's finish our data science methods overview by getting a brief overview of machine learning. Now, I got to admit, when you say the term machine learning, people start thinking about something like the robot overlords who are going to take over the world. That's not what it is. Instead, let's go back to our Venn diagram one more time. And in the intersection at the top between coding and stats is machine learning, or as it's commonly called, is just ML. The goal of machine learning is to go and work in a data space. So you can, for instance, take a whole lot of data. I've got tons of books here. And then you can reduce the dimensionality. That is, take a very large scattered data set and try to find the most essential parts of that data. And then you can use these methods to find clusters within the data, like goes with like. You can use methods like k-means. You can also look for anomalies or unusual cases that show up in the data space. Or if we go back to categories, again, I talked about like for like. You can use things like logistic regression or k nearest neighbors, KNN. You can use naive Bayes for classification, or decision trees, or SVM, which is support vector machines, or artificial neural nets. Any of those will help you find the patterns and the clumping in your data so you can get similar cases next to each other and get the cohesion that you need to make conclusions about these groups. Also, a major element of machine learning is predictions. You're going to point your way down the road. The most common approach here, the most basic, is linear regression, multiple regression. There's also Poisson regression, which is used for modeling count or frequency data. And then there's the issue of ensemble models, where you create several models and you take the predictions from each of those and you put them together to get an overall more reliable prediction. Now, I'll talk about each of these in a little more detail in later courses, but for right now, I mostly just want you to know that these things exist, and that's what we mean when we refer to machine learning. So, in sum, machine learning can be used to categorize cases and to predict scores on outcomes. And there's a lot of choices, many choices and procedures available. But again, as I said with statistics, and as I'll say again many times after this, no matter what, the goal is not that I'm going to do an artificial neural network or an SVM. The goal is to get useful insight into your data. Machine learning is a tool, and use it to the extent that it helps you get that insight that you need. In the last several videos, I've talked about the role in data science of technical things. On the other hand, communicating is also central to the practice. And the first thing I want to talk about there is interpretability. The idea here is that you want to be able to lead people through a path on your data. You want to tell a data-driven story. And that's the entire goal of what we're doing with data science. Now, another way to think about this is when you're doing your analysis, what you're trying to do is solve for value. You're making an equation, you take the data, you're trying to solve for value. The trouble is this: a lot of people get hung up on analysis, but they need to remember that analysis is not the same thing as value. Instead, I like to think of it this way, that analysis times story is equal to value. Now, please note, that's multiplicative, not additive. And so one consequence of that is when you go back to analysis times story equals value, well, If you have zero story, you're going to have zero value because, as you recall, anything times zero is zero. So instead of that, let's go back this and say what we really want to do is we want to maximize the story so that we can maximize the value that results from our analysis. Again, maximum value is the overall goal here. The analysis, the tools, the tech are simply methods for getting to that goal. So let's talk about goals, for instance. Analysis is goal-driven. You're trying to accomplish something in specific, and so the story or the narrative or the explanation you give about your project should match those goals. If you're working for a client and they had a specific question that they wanted you to answer, then you have a professional responsibility to answer those questions clearly and unambiguously so they know whether you said yes or no and they know why you said yes or no. Now, part of the problem here is the fact that the client isn't you and they don't see what you do. And as I show here, simply covering your face doesn't make things disappear. You have to worry about a few psychological abstractions. You have to worry about egocentrism. And I'm not talking about being vain. I'm talking about the idea that you think other people see and know and understand what you know. That's not true. Otherwise, they wouldn't have hired you in the first place. And so you have to put it in terms that the client works with and that they understand. And you're going to have to get out of your own center in order to do that. Also, there's the idea of false consensus, the idea that, well, everybody knows that. And again, that's not true. Otherwise, they wouldn't have hired you. You need to understand that they're going to come from a different background with a different range of experience and interpretation. You're going to have to compensate for that. A funny little thing is the idea about anchoring. When you give somebody an initial impression, they use that as an anchor and then they adjust away from it. So if you're going to try to flip things over on their heads, watch out for giving a false impression at the beginning, unless you absolutely need to. But most importantly, in order to bridge the gap between the client and you need to have clarity and explain yourself at each step. You can also think about the answers. When you're explaining the project to the client, you might want to start in a very simple procedure. State the question that you're answering. Give your answer to that question. And if you need to, qualify as needed, and then go in order top to bottom. So you're trying to make it as clear as possible what you're saying, what the answer is, and make it really easy to follow. Now, in terms of discussing your process, how you did this all, most of the time, it's probably the case that they don't care. They just want to know what the answer is and that you used a good method to do that. So in terms of discussing process or the technical details, only when absolutely necessary. That's something to keep in mind. The process here is to remember that analysis, which means breaking something apart. This, by the way, is a mechanical typewriter broken into its individual components. Analysis means to take something apart. An analysis of data is an exercise in simplification. You're taking the overall complexity, sort of the overwhelmingness of the data, and you're boiling it down and finding the patterns that make sense and serve the needs of your client. Now, let's go to a wonderful quote from our friend Albert Einstein here, who said, "Everything should be made as simple as possible, but not simpler." That's true in presenting your analysis. Or, if you want to go see the architect and designer Ludwig Mies van der Rohe, who said, "Less is more." It's actually Robert Browning who originally said that, but Mies van der Rohe popularized it. Or if you want another way of putting a principle that comes from my field, I'm actually a psychological researcher. They talk about being minimally sufficient, just enough to adequately answer the question. If you're in commerce, you know about a minimal viable product. It's sort of the same idea with an analysis here, the minimum viable analysis. So here's a few tips. When you're giving a presentation, more charts, less text. Great. And then simplify the charts. Remove everything that doesn't need to be in there. Generally, you want to avoid tables of data because those are hard to read. And then one more time, because I want to emphasize it, less text. Again, charts, tables can usually carry the message. And so let me give you an example here. I'm going to give a very famous data set, Berkeley admissions. Now, these are not stairs to Berkeley, but it gives the idea of trying to get into something that's far off and distant. Here's the data. This is graduate school admissions in 1973. So it's over 40 years ago. But the idea is that men and women were both applying for graduate school at the University of California at Berkeley. And what we found is that 44% of the men who applied were admitted. That's their part in green. And that of the women, only 35% were admitted when they applied. So really, at first glance, this is bias, and it actually led to a lawsuit. It was a major issue. So what Berkeley then tried to do is find out, well, which programs are responsible for this bias? And then you got a very curious set of results. If you break the applications down by program, and here we're just calling them A through F, 6 different programs, what you find actually is that in each of these, male applicants are on the left, female applicants are on the right. If you look at program A, women actually got accepted at a higher rate. And the same is true for B. And the same is true for D. And the same is true for F. And so this is a very curious set of responses, and it's something that requires explanation. Now in statistics, this is known as Simpson's paradox. But here's the paradox. Bias may be negligible at the department level. And in fact, as we saw in 4 of the departments, there was a possible bias in favor of women. And the problem is that women applied to more selective programs with lower acceptance rates. Now, some people stop right here and say, therefore, nothing's going on, nothing to complain about. But that's still ending the story a little bit early. There are other questions that you can ask. And as producing a data-driven story, this is stuff that you would want to do. So for instance, you may want to ask, why do the programs vary in overall class size? Why do the acceptance rates differ from one program to the other? Why do men and women apply to different programs? And you might want to look at things like the admissions criteria for each of the programs, the promotional strategies, how they advertise themselves to students. You might want to look at the kinds of prior education students have in each of the programs, and you really want to look at funding levels for each of the programs. And so really you get one answer. It leads to more questions, maybe some more answers and more questions. And you need to address enough of this to provide a comprehensive overview and solution to it for your client. In sum, let's say this: stories give value to data analyses. And when you tell the story, you need to make sure that you are addressing your client's goals in a clear, unambiguous way. And the overall principle here is be minimally sufficient. Get to the point, make it clear, say what you need to, but otherwise be concise and make your message clear. The next step in discussing data science and communicating is to talk about actionable insights, or information that can be used productively to accomplish something. Now, to give sort of a bizarre segue here, you look at a game controller. It may be a pretty thing, it may be a nice object, but remember, game controllers exist to do something. They exist to help you play the game and to do it as effectively as possible. They have a function, they have a purpose. Same way, data is for doing. Now that's a paraphrase from one of my favorite historical figures, and this is William James, the father of American psychology and pragmatism in philosophy. And he has this wonderful quote. He said, "My thinking is first and last and always for the sake of my doing." And the idea applies to analysis. Your analysis and your data is for the sake of your doing. And so you're trying to get some sort of specific insight in how you should proceed. What you want to avoid is the opposite of this from one of my other favorite cultural heroes, the famous Yankees catcher, Yogi Berra, who said, "We're lost, but we're making good time." And so the idea here is that frantic activity does not make up for a lack of direction. You need to understand what you're doing so you can reach the particular goal. And your analysis is supposed to do that. So when you're giving your analysis, you're going to try to point the way. Remember, why was the project conducted? The goal is usually to direct some kind of action, reach some kind of goal for your client, and that the analysis should be able to guide that action in an informed way. One thing you want to do is you want to be able to give the next steps to your client. Give the next steps. Tell them what they need to do now. You want to be able to justify each of those recommendations with the data and your analysis. As much as possible, be specific, tell them exactly what they need to do. Make sure it's doable by the client, that it's within their range of capability, and that each step should build on the previous step. Now, that being said, there is one really fundamental sort of philosophical problem here, and that's the difference between correlation and causation. Basically, it goes this way. Your data gives you correlation. You know that this is associated with that. But your client doesn't simply want to know what's associated. They want to know what causes something. Because if they're going to do something, that's an intervention. It's designed to produce a particular result. So really, how do you get from the correlation, which is what you have in the data, to the causation, which is what your client wants? Well, there's a few ways to do that. One is experimental studies. These are randomized controlled trials. Now, that's theoretically the simplest path to causality, but it can be really tricky in the real world. There are quasi-experiments, and these are methods, a whole collection of methods, that use non-randomized data, usually observational data, adjusted in particular ways to get an estimate of causal inference. Or there's the theory and experience, and this is research-based theory and domain-specific experience. And this is where you actually get to rely on your client's information. They can help you interpret the information, especially if they have greater domain expertise than you do. Another thing to think about are the social factors that affect your data. Now, you remember the data science Venn diagram. We've looked at it lots of times. It's got these three elements. Some people have proposed adding a fourth circle to this Venn diagram, and we'll kind of put that in there and say that social understanding is also important, critical really, to valid data science. Now, I love that idea, and I do think that it's important to understand how things are going to play out. There's a few kinds of social understanding. You want to be aware of your client's mission. You want to make sure that your recommendations are consistent with your client's mission. Also, that your recommendations are consistent with your client's identity, not just this is what we do, but this is really who we are. You need to be aware of the business context, sort of the competitive environment and the regulatory environment that they're working in, as well as the social context. And that can be outside of the organization, but even more often within the organization. Your recommendations will affect relationships within the client's organization. And you're going to try to be aware of those as much as you can to make it so that your recommendations can be realized the way they need to be. So in sum, data science is goal focused. And when you're focusing on that goal for your client, you need to give specific next steps that are based on your analysis and justifiable from the data. And in doing so, be aware of the social, political, and economic context that gives you the best opportunity of getting something really useful out of your analysis. When you're working in data science and trying to communicate your results, presentation graphics can be an enormously helpful tool. Think of it this way. You are trying to paint a picture for the benefit of your client. Now, when you're working with graphics, there can be a couple of different goals. It depends on what kind of graphics you're working with. There's the general category of exploratory graphics. These are ones that you are using as the analyst. And for exploratory graphics, you need speed and responsiveness. And so you get very simple graphics. This is a base histogram in R, and they can get a little more sophisticated. And this is done in ggplot, and then you can break it down in a couple of histograms, or you can make it a different way, or make them see-through, or split them apart into small multiples. But in each case, this is done for the benefit of you as the analyst understanding the data. These are quick, they're effective. Now, they're not very well labeled, and they're usually for your insight, and then you do other things as a result of that. On the other hand, presentation graphics, which are for the benefit of your client, those need clarity and they need a narrative flow. Now, let me talk about each of those characteristics very briefly. Clarity versus distraction. There are things that can go wrong in graphics. Number one is colors. Colors can actually be a problem. Also, three-dimensional or false third dimensions are nearly always a distraction. One that gets a little touchy for some people is interaction. We think of interactive graphics as really cool, great things to have. but you run the risk of people getting distracted by the interaction and start playing around with it and go like, ooh, I press here, it does that. And that distracts from the message. So actually, it may be important to not have interaction. And then the same thing is true of animation. Flat static graphics can often be more informative because they have fewer distractions in them. Let me give you a quick example of how not to do things. Now, this is a chart that I made. I made it in Excel and I did it based on some of the mistakes I've seen in graphics submitted to me when I teach. And I guarantee you everything in here I have seen in real life, just not necessarily combined all at once. Let's zoom in on this a little bit so we can see the full badness of this graphic. And let's see what's going on here. We've got a scale here that starts at 8, goes to 28%, and it's tiny, doesn't even cover the range of the data. We've got this bizarre picture on the wall. We have no axis lines on the walls. We come down here, the labels for educational levels are in alphabetical order instead of the more logical higher levels of education. Then we've got the data represented as cones, which are difficult to read and compare, and it's only made worse by the colors and the textures. You know, if you want to take an extreme, this one for grad degrees doesn't even make it to the floor value of 8%. And this one for high school grad is cut off at the top at 28%. And this, by the way, is a picture of a sheep, and people do this kind of stuff and it drives me crazy. If you want to see a better chart with the exact same data, this is it right here. It's a straight bar chart. It's flat. It's as simple. It's as clean as possible. And this is better in many ways. Most effective here is that it communicates clearly. There's no distractions. It's a logical flow. This is going to get the point across so much faster. And I can give you another example of it. Here's a chart I showed previously about salaries for incomes. I have a list here. I've got data scientists in it. If I want to draw attention to it, I have the option of like putting a circle around it, and I can put a number next to it to explain it. That's one way to make it easy to see what's going on. But you don't even have to get fancy. You know, I just got out a pen and a Post-it note and I drew a bar chart of some real data about life expectancy. This tells the story as well that there is something terribly amiss in Sierra Leone. But now let's talk about creating narrative flow in your presentation graphics. To do this, I'm going to pull some charts from my most cited academic paper, which is called A Third Voice, a review of empirical research on the psychological outcomes of restorative justice. Think of that as mediation for juvenile crimes, mostly juvenile. And this paper is interesting because really it's about 14 bar charts with just enough text to hold them together. And you can see there's a flow. The charts are very simple. This is judgments about whether the criminal justice system was fair. The 2 bars on the left are victims. The 2 bars on the right are offenders. And for each group, on the left are people who participated in restorative justice or victim offender mediation or mediation for crimes. And for each set on the right are people who went through standard criminal procedures. It says court, but it usually means plea bargaining. Anyhow, it's really easy to see that in both cases, restorative justice bar is higher. People were more likely to say it was fair. They also felt that they had an opportunity to tell their story. That's one reason they might think it's fair. They also felt the offender was held accountable more often. In fact, if you go to court on the offenders, that line's below 50%, and that's the offenders themselves making the judgment. Then you can go to forgiveness and apologies. And again, this is actually a simple thing to code, and you can see there's an enormous difference. And in fact, one of the reasons there's such a big difference is because in standard court proceedings, the offender very rarely meets the victim. Now, it also turns out that I need to qualify this a little bit because a bunch of the studies included drunk driving with no injuries or accidents. When we take them out, we see a huge change. And then we can go to whether a person's satisfied with the outcome. Again, we see an advantage for restorative justice. Whether the victim is still upset about the crime, now the bars are a little different. And whether they're afraid of re-victimization, that's over a 2-to-1 difference. And then finally, recidivism for offenders or reoffending. And you see a big difference there. And so what I have here is a bunch of charts that are very, very simple to read, and they kind of flow in how they're giving the overall impression and then detailing it a little bit more. There's nothing fancy here. There's nothing interactive. There's nothing animated. There's nothing kind of flowing in 17 different directions. It's easy, but it follows a story and it tells a narrative about the data. And that should be your major goal with presentation graphics. In sum, presenting, or the graphics that you use for presenting, are not the same as the graphics you use for exploring. They have different needs and different goals. But no matter what you're doing, be clear in your graphics and be focused in what you're trying to tell. And above all, create a strong narrative that gives a different level of perspective and answers questions as you go, to anticipate a client's question and to give them the most reliable, solid information and the greatest confidence in your analysis. The final element of data science and communicating that I wanted to talk about is reproducible research. And you can think of it as this idea. You want to be able to play that song again. And the reason for that is data science projects are rarely one and done. Rather, they tend to be incremental, they tend to be cumulative, and they tend to adapt to the circumstances that they're working in. So one of the important things here, probably if you want to summarize it very briefly, is this: show your work. There's a few reasons for this. You may have to revise your research at a later date, your own analyses. You may be doing another project and you want to borrow something from previous studies. More likely, you'll have to hand it off to somebody else at a future point, and they're going to have to be able to understand what you did. And then there's the very significant issue in both scientific and economic research of accountability. You have to be able to show that you did things in a responsible way and that your conclusions are justified. That's for clients, funding agencies, regulators, academic reviewers, any number of people. Now, you may be familiar with the concept of open data, but you may be less familiar with the concept of open data science, and that's more than open data. So for instance, I'll just let you know that there is something called the Open Data Science Conference at odsc.com, and it meets 3 times a year in different places. And this is entirely, of course, devoted to open data science, using both open data, but making the methods transparent to people around them. One thing that can make this really simple is something called the Open Science Framework, which is at osf.io. It's a way of sharing your data and your research with an annotation of how you got through the whole thing with other people. It makes the research transparent, which is what we need. One of my professional organizations, the Association for Psychological Science, has a major initiative on this called Open Practices, where they are strongly encouraging people to share their data as much as is ethically permissible, and to absolutely share their methods before they even conduct the study, as a way of getting rigorous intellectual honesty and accountability. Now, another step in all of this is to archive your data, make that information available, put it on the shelf. And what you want to do here is you want to archive all of your data sets, both the totally raw before you did anything with a data set, and every step in process until your final clean data set. Along with that, you want to archive all of the code that you used to process and analyze the data. If you used a programming language like R or Python, that's really simple. If you used a program like SPSS, you need to save the syntax files, and then it can be done that way. And again, no matter what, make sure to comment liberally and explain yourself. Now, part of that is you need to be able to explain your process, because you're not just this lone person sitting on the sofa working by yourself. You're with other people, and you need to explain why you did it the way that you did. You need to explain the choices, the consequences of those choices, the times that you had to backtrack and try it over again. This all also works into the principle of future-proofing your work. You want to do a few things here. Number one, the data. You want to store the data in non-proprietary formats like a CSV or comma separated values file, because anything could read CSV files. If you stored it in the proprietary SPSS.save format, you might be in a lot of trouble when somebody tries to use it later and they can't open it. Also, there's storage. You want to place all of your files in a secure, accessible location like GitHub. It's probably one of the best choices. And then the code, you may want to use something like a dependency management package like PackRat for R or virtual environment for Python as a way of making sure that the packages that you use, that there are always versions that work, because sometimes things get updated and it gets broken. This is a way of making sure that the system that you have will always work. Overall, you can think of this too. You want to explain yourself, and a neat way to do that is to put your narrative in a notebook. Now, you can have a physical lab book, but you can also do digital books. A really common one, especially if you're using Python, is Jupyter with a Y there in the middle. The Jupyter notebooks are interactive notebooks. So here's a screenshot of a very simple one I made in Python. And you have titles, you have text, you have the graphics. If you're working in R, you can do this through something called R Markdown, which works in the same way. You do it in RStudio, use Markdown, and you can annotate the whole thing. Get more information about that at rmarkdown.rstudio.com. And so for instance, here's an R analysis I did, and you see the code on the left and you see the Markdown version on the right. What's neat about this is that this little bit of code here, this title and this text and this little bit of R code then is displayed as this formatted heading, as this formatted text, and this turns into the entire R output right there. It's a great way to do things. And then if you do R Markdown, you actually have the option of uploading the document into something called RPubs. And that's an online document that can be made accessible to anybody. Here's the same document. And if you want to go see it, you can go to this address. It's kind of long, so I'm going to let you write that one down yourself. But in sum, here's what we have. You want to do your work and archive the information in a way that supports collaboration. Explain your choices, say what you did, show how you did it. This allows you to future-proof your work so that it will work in other situations and for other people. And as much as possible, no matter how you do it, make sure to share your narrative so people understand your process and they can see that your conclusions are justifiable, strong, and reliable. Now, something that I've mentioned several times when talking about data science, and I'll do it again in this conclusion, is that it's important to give people next steps. So I'm going to do that for you right now. If you're wondering what to do after having watched this very general overview course, I can give you a few ideas. Number one, maybe you want to start trying to do some coding in R or Python. We have courses for those. You might want to try doing some data visualization, one of the most important things that you can do. You may want to brush up on statistics and maybe some math that goes along with it. And you may want to try your hand at machine learning. All of these will get you up and rolling in the practice of data science. You can also try looking at data sourcing, find the information that you're going to do. But no matter what happens, try to keep it in context. So for instance, data science can be applied to marketing and sports and health and education and the arts and really a huge number of other things. And we will have courses here at datalab.cc that talk about all of those. You may also want to start getting involved in the community of data science. One of the best conferences that you can go to is O'Reilly Strata, which meets several times a year around the globe. There's also Predictive Analytics World, again, several times a year around the world. Then there's much smaller conferences. I love Tapestry or tapestryconference.com, which is about storytelling in data science. And Extract, a one-day conference about data stories that's put on by Import.io, one of the great data sourcing applications that's available for scraping web data. If you want to start working with actual data, a great choice is to go to Kaggle.com. And they sponsor data science competitions, which actually have cash rewards, but there's also wonderful data sets you can work with there to find out how they work and compare your results to those of other people. And once you're feeling comfortable with that, you may actually try turning around and doing some service. Datakind.org is the premier organization for data science as humanitarian service. They do major projects around the world. I love their examples. There are other things you can do. There's an annual event called Do Good Data. And then datalab.cc will be sponsoring twice a year Datalab Charrettes, which are opportunities for people in the Utah area to work with local nonprofits on their data. But above all of this, I want you to remember this one thing. Data science is fundamentally democratic. It's something that everybody needs to learn to do in some way, shape, or form. The ability to work with data is a fundamental ability, and everybody would be better off by learning to work with data intelligently and sensitively. Or to put it another way, data science needs you. Thanks so much for joining me for this introductory course. I hope it's been good, and I look forward to seeing you in the other courses here at datalab.cc. Welcome to Data Sourcing. I'm Barton Poulsen, and in this course, we're going to talk about data opus, or that's Latin for data needed. The idea here is that no data science, and that is a sad thing. So instead of leaving it at that, we're going to use this course to talk about methods for measuring and evaluating data, and methods for accessing existing data, and even methods for creating new custom data. Take those together, and it's a happy situation. At the same time, we'll do all of this still at an accessible, conceptual, and non-technical level, because the technical hands-on stuff will happen in later other courses. But for now, let's talk data. For data sourcing, the first thing we want to talk about is measurement. And within that category, we're going to talk about metrics. The idea here is that you actually need to know what your target is if you want to have a chance to hit it. There's a few particular reasons for this. First off, data science is action-oriented. The goal is to do something as opposed to simply understand something, which I say as an academic practitioner. Also, your goal needs to be explicit, and that's important because the goals can guide your effort. So you want to say exactly what you're trying to accomplish so you know when you get there. Also, goals exist for the benefit of the client because they can prevent frustration. They know what you're working on. They know what you have to do to get there. And finally, the goals and the metrics exist for the benefit of the analyst because they help you use your time well. You know when you're done, you know when you can move ahead with something, and that makes everything a little more efficient and a little more productive. Now, when we talk about this, the first thing you want to do is try to define success in your particular project or domain. Depending on where you are in commerce, that can include things like sales or click-through rates or new customers. In education, it can include scores on tests. It can include graduation rates or retention. In government, it can include things like housing and jobs. In research, it can include the ability to serve the people that you're trying to better understand. So whatever domain you're in, there will be different standards for success, and you're going to need to know what applies in your domain. Next are specific metrics or ways of measuring. Now, again, there are a few different categories here. There are business metrics. There are key performance indicators or KPIs. There are SMART goals, that's an acronym. And there's also the issue of having multiple goals. I'll talk about each of those for just a second now. First off, let's talk about business metrics. If you're in the commercial world, there are some common ways of measuring success. A very obvious one is sales revenue. Are you making more money? Are you moving the merchandise? Are you getting sales? Also, there's the issue of leads generated, new customers or new potential customers, because that then in turn is associated with future sales. There's also the issue of customer value or lifetime customer value. So you may have a small number of customers, but they all have a lot of revenue, and you can use that to really predict the overall profitability of your current system. And then there's churn rate, which has to do with losing and gaining new customers and having a lot of turnover. So any of these are potential ways of defining success and measuring it. These are potential metrics. There are others, but these are some really common ones. Now, I mentioned earlier something called a key performance indicator or KPI. KPIs come from David Parmenter, and he's got a few ways of describing them. He says a key performance indicator for business, number one, should be non-financial. So not just the bottom line, but something else that might be associated with it or that measures the overall productivity of the association. They should be timely, for instance, weekly, daily, or even constantly gathered information. They should have a CEO focus. So the senior management team are the ones who generally make the decisions that affect how the organization acts on the KPIs. They should be simple. So everybody in the organization, everybody knows what they are and knows what to do about them. They should be team-based, so teams can take joint responsibility for meeting each one of the KPIs. They should have significant impact. What that really means is they should affect more than one important outcome. So you can do profitability and market reach, or improved manufacturing time and fewer defects. And finally, an ideal KPI has a limited dark side. That means there's fewer possibilities for reinforcing the wrong behaviors and rewarding people for sort of exploiting the system. Next, there are SMART goals, where SMART stands for specific, measurable, assignable to a particular person, realistic, meaning you can actually do it with the resources you have at hand, and time bound, so you know when it can get done. So whenever you form a goal, you should try to assess it on each of these criteria. And that's a way of saying that this is a good goal to be used as a metric for the success of our organization. Now, the trick, however, is when you have multiple goals, multiple possible endpoints. And the reason that's difficult is because, well, it's easy to focus on one goal if you're just trying to maximize revenue, or if you're just trying to maximize, graduation rate. There's a lot of things you can do. It becomes more difficult when you have to focus on many things simultaneously, especially because some of these goals may conflict. The things that you do to maximize one may impair the other. And so when that happens, you actually need to start engaging in a deliberate process of optimization. You need to optimize. And there are ways that you can do this. If you have enough data, you can do mathematical optimization to find the ideal balance of efforts to pursue one goal and the other goal at the same time. Now, this is a very general summary, and let me finish with this. In sum, metrics or methods for measuring can help awareness of how well your organization is functioning and how well you're reaching your goals. There are many different methods available for defining success and measuring progress towards those things. The trick, however, comes when you have to balance efforts to reach multiple goals simultaneously, which can bring in the need for things like optimization. When talking about data sourcing and measurement, one very important issue has to do with the accuracy of your measurements. The idea here is that you don't want to have to throw away all your ideas. You don't want to waste effort. One way of doing this in a very quantitative fashion is to make a classification table. So what that looks like is this. You talk about, for instance, positive results, negative results. And in fact, let's start by looking at the top here. The middle two columns here talk about whether an event is present, whether your house is on fire, whether a sale occurs, whether you've got a tax evader, whatever. So that's whether a particular thing is actually happening or not. On the left here is whether the test or the indicator suggests that a thing is or is not happening. And then you have these combinations of true positives, where the test says it's happening and it really is, and false positive, where the test says it's happening but it's not. And then below that, true negatives, where the test says it isn't happening and that's correct. And then false negatives, where the test says there's nothing going on, but there is in fact the event occurring. And then you start to get the column totals, the total number of events present or absent, and the row totals that talk about the test results. Now, from this table, what you get is 4 kinds of accuracy, or really 4 different ways of quantifying accuracy using different standards. And they go by these names: sensitivity, specificity, positive predictive value, and negative predictive value. I'll show you very briefly how each of them works. Sensitivity can be expressed this way. If there's a fire, does the alarm ring? You want that to happen. And so that's a matter of looking at the true positives and dividing that by the total number of alarms. So the test positive means there's an alarm, and the event present means there's a fire. You want always to have an alarm when there's a fire. Specificity, on the other hand, is sort of the flip side of this. If there isn't a fire, does the alarm stay quiet? This is where you're looking at the ratio of true negatives to total absent events, where there's no fire and the alarm's not ringing, and that's what you want. Now, those are looking at columns. You can also go sideways across rows. So the first one there is positive predictive value, often just abbreviated as PPV. And we flip around the order a little bit. This one says, if the alarm rings, was there a fire? So now you're looking at the true positives and dividing it by the total number of positives. Total number of positives is any time the alarm rings. True positives is because there was a fire. And negative predictive value, or NPV, says if the alarm doesn't ring, does that in fact mean that there is no fire? Well, here you're looking at true negatives and dividing it by total negatives the time that it doesn't ring. And again, you want to maximize that so the true negatives account for all of the negatives, the same way you want the true positives to account for all of the positives, and so on. Now, you can put numbers on all of these going from 0% to 100%, and the idea is to maximize each one as much as you can. So in sum, from these tables, we get 4 kinds of accuracy, and there's a different focus for each one, but the same overall goal. You want to identify the true positives and true negatives and avoid the false positives and false negatives. And this is one way of putting numbers on, an index really, on the accuracy of your measurement. Now, data sourcing may seem like a very quantitative topic, especially when we're talking about measurement, but I want to measure one important thing here, and that is the social context of measurement. The idea here really is that people are people, and they all have their own goals and they're going their own ways, and we all have our own thoughts and feelings that don't always coincide with each other, and this can affect measurement. And so, for instance, when you're trying to define your goals and you're trying to maximize them, you want to look at things like, for instance, the business model. An organization's business model, the way they conduct their business, the way they make their money, is tied to its identity and its reason to be. And if you make a recommendation that's contrary to their business model, that can actually be perceived as a threat to their core identity, and people tend to get freaked out in that situation. Also, restrictions. So for instance, there may be laws, policies, and common practices both organizationally and culturally that may limit the ways that goals can be met. Now, most of these make a lot of sense. So the idea is you can't just do anything you want. You need to have these constraints. And when you make your recommendations, maybe you'll work creatively in them as long as you're still behaving legally and ethically. But you do need to be aware of these constraints. Next is the environment. And the idea here is that competition occurs both between organizations. That company here is trying to reach a goal, but they're competing with company B over there. But probably even more significantly, there is competition within the organization. This is really a recognition of office politics, and that when you as a consultant make a recommendation based on your analysis, you need to understand you're kind of dropping a little football into the office, and things are going to further one person's career, maybe to the detriment of another. And in order for your recommendations to have the maximum effectiveness, they need to play out well in the office. That's something that you need to be aware of as you're making your recommendations. Finally, there's the issue of manipulation. And a sad truism about people is that any reward system at all, will be exploited, and people will generally game the system. This happens especially when you have a strong cutoff. You need to get at least 80% or you get fired. And people will do anything to make their numbers appear to be 80%. This happens an awful lot when you look at executive compensation systems. It looks a lot when you have very high stakes school testing. It happens in an enormous number of situations. And so you need to be aware of the risk of exploitation and gaming. Now, don't think then that all is lost. Don't give up. You can still do really wonderful assessment. You can get good metrics. Just be aware of these particular issues and be sensitive to them as you both conduct your research and as you make your recommendations. So, in sum, social factors affect goals, and they affect the way that you meet those goals. There are limits and consequences both on how you reach the goals and how really what the goals should be. And that when you're making advice on how to reach those goals, please be sensitive to how things play out with metrics and how people will adapt their behavior to meet the goals. That way, you can make something that's more likely to be implemented the way you meant and more likely to predict accurately what can happen with your goals. When it comes to data sourcing, obviously the most important thing is to get data, but the easiest way to do that, at least in theory, is to use existing data. Think of it as going to the bookshelf and getting the data that you have right there at hand. Now, there's a few different ways to do this. You can get in-house data, you can get open data, and you can get third-party data. Another nice way to think of that is proprietary, public, and purchased data, the 3 Ps I've heard it called. Let's talk about each of these a little bit more. So in-house data, that's stuff that's already in your organization. What's nice about that is it can be really fast and easy. It's right there. And the format may be appropriate for the kind of software and the computer that you're using. If you're fortunate, there's good documentation, although sometimes when it's in-house, people just kind of throw it together. So you have to watch out for that. And there's the issue of quality control. Now, this is true with any kind of data, but you need to pay attention with in-house because you don't know the circumstances necessarily under which people gathered the data and how much attention they were paying to something. There's also an issue of restrictions. There may be some data that while it's in-house, you may not be allowed to use, or you may not be able to publish the results or share the results with other people. So these are things that you need to think about when you're going to use in-house data in terms of how can you use it to facilitate your data science projects. Specifically, there are a few pros and cons. In-house data, potentially quick, easy, free. Hopefully it's standardized. Maybe even the original team that conducted this study is still there. And you might have identifiers in the data which make it easier for you to do an individual level analysis. On the con side, however, the in-house data simply may not exist. Maybe it's just not there. Or the documentation may be inadequate. And of course, the quality may be uncertain. It's always true, but maybe something you have to pay more attention to when you're using in-house data. Now, another choice is open data, like going to the library and getting something. This is prepared data that's freely available. It consists of things like government data and corporate data and scientific data from a number of sources. Let me show you some of my favorite open data sources, just so you know where they are and that they exist. Probably the best one is data.gov here in the US. That is it says right here, the home of the US government's open data. Or you may have a state level one. For instance, I'm in Utah and we have data.utah.gov, also a great source of more regional information. If you're in Europe, you have open-data.europa.eu, the European Union Open Data Portal. And then there are major nonprofit organizations. So the UN has unicef.org/statistics for their statistical and monitoring data. The World Health Organization has the Global Health Observatory at who.int/GHO. And then there are private organizations that work in the public interest, such as the Pew Research Center, which shares a lot of its data sets, and the New York Times, which makes it possible to use APIs to access a huge amount of the data of things they've published over a huge time span. And then two of the mother loads, there's Google, which at google.com has public data, which is a wonderful thing. And then Amazon at aws.amazon.com datasets has gargantuan datasets. So if you needed a dataset that was like 5 terabytes in size, this is the place that you would go to get it. Now, there's some pros and cons to using this kind of open data. First is that you can get very valuable datasets that maybe cost millions of dollars to gather and to process. And you can get a very wide range of topics and times and groups of people and so on. And often the data is very well formatted and well documented. There are, however, a few cons. Sometimes there's bias samples. Say, for instance, you only get people who have internet access, and that can mean, not everybody. Sometimes the meaning of the data is not clear, or it may not mean exactly what you want it to. A potential problem is that sometimes you may need to share your analyses. And if you're doing proprietary research, well, it's going to have to be open research instead. And so that can create a crimp with some of your clients.